In this video, we're going to start our discussion of enzymes. And so, first we're just going to look at the differences between an enzyme and a chemical catalyst you might see in organic or inorganic. Now, both enzymes and chemical catalysts are catalysts, but the big differences are that enzymes are generally way faster than your chemical catalysts, several orders of magnitude, so hundreds, thousands, 10,000, 100,000 times faster, millions, billions, trillions, way faster. The conditions for these reactions are much milder. So your temperature is below 100, you're at atmospheric pressure, neutral pH, while chemical catalysts, you need high temperatures, acidic, basic, high pressure, you need very odd conditions for those to happen. You have a great reaction specificity. You really never have a side product if you're using an enzyme. You get what you get always. And they can be regulated quite easily, either with concentration or other substances. This is called allosteric control. You have a substance bind that's not your normal substrate, and it inhibits your enzyme. It's being controlled allosterically. You can also control it through covalent modifications like a phosphate, or just by changing the amount of enzyme. If you don't want a reaction to work inside your cell, you can just get rid of that enzyme and that reaction won't run. Now, the way we classify enzymes is basically how they, or what type of reaction they do. First off, enzymes will usually end in the word "ase", and the common name will describe what it does. For example, urease will work on urea. Alcohol dehydrogenase will work on ethanol. Not always, though. You have enzymes like catalase. You could never guess what catalase does. Normally, though, in the last couple decades, people have gotten better at that. But when you first started studying enzymes, it was the Wild West. So now enzymes, we have a naming system for them. First, we classify them based on the reaction that they do. So we have 6 major classes. So oxidoreductases, transferases, hydrolysases, lyases, isomerases, and ligases. For each of these classes, we have subclasses. For each of your subclasses, you have a subclass. So enzymes get 2 names in a 4-part classification system. So you get your accepted, recommended name, and then your systematic name. And the enzyme classification system is usually only used in internet databases. For example, an enzyme could be called EC 4.2.1.3. So EC means the enzyme commission. The class, so this is a lyase. It's the first subclass of lyase, and the second subclass of lyase, the first subclass, and the third enzyme of that specific type. So you can see it's an easy way to categorize enzymes. The people usually will talk about the enzyme recommended name when you talk about them in science. No one's going to come up to you and say, I'm studying at 4.2.1.3 and expect you to know what they're talking about. Now, enzymes, like I said, will only usually work on specific substances. And the way it can distinguish different substances is because you have a nice fit through non-covalent interactions. So no covalent bonds are forming. You only have van der Waals interactions, electrostatic interactions, hydrogen bonds, hydrophobic effects. And the substrate and enzyme binding, not only does it fit geometrically, but you also have electronic complementarity between the substrate and enzyme. That is, positive will go with a positive, negative with a negative, hydrogen bond with a hydrogen bond. So that's what's being shown here. This H and H minus H are from the substrate. So when it binds, you have a negative going with a positive. Your NH going with an oxygen, hydrophobic going with hydrophobic. So it's a good fit. Now, when we talk about substrates and enzymes interacting, we have 2 different models. One, the induced fit model, which is more popular now, in that the substrate and enzyme bind okay, but the energy from binding will change how the enzyme looks like. So upon binding, the substrate undergoes change. The lock and key model says it's a perfect fit, like a lock and a key are a perfect fit. This model is falling out of favor, but we can still use it to think about how enzymes work. So enzymes are very stereospecific. That is, they bind only one type of chiral substrate, and they will only give one type of chiral product. And this is because we only have L amino acids, so your active sites are asymmetric. If you have both L and R amino acids, you could spit out different stereospecific products. So an example of this comes from ATP, the Krebs cycle citrate will go to isocitrate or citrate with a conatase, and the chirality of citrate going in will always be the same. It will not work on the other version. And the version of isocitrate that always comes out will always be the same. You will not get an achiral, or you will not get a racemic mixture. You will always get the same chirality out. That's how enzymes work. So a lot of enzymes only work on one substrate. Some enzymes will actually allow different substrates to bind. And in fact, most enzymes can catalyze reactions based on a small range of compounds that look the same. Your efficiencies just will be different. So enzymes usually want one type of substrate, but can work on others. Take alcohol dehydrogenase, for example. So alcohol dehydrogenase usually takes ethanol and turns into acetaldehyde. It does this faster than taking methanol to formaldehyde or isopropanol to acetone. Although it will do this, it'll just be super slow. You also have digestive enzymes that will do this. So chymotrypsin works on a peptide much faster than it does on an ester. And they're similar, and it will cut both, but it'll just do it to a peptide much faster. Now, some enzymes need other molecules to work completely, and we call these cofactors. So we call these molecular teeth because without these, you're not going to do a reaction, just like you're not going to chew food without teeth. One type of cofactor are metal ions, copper, iron, and zinc being common. That's why you need those in your diet. And cadmium and mercury are poisonous to us because they will replace zinc in your enzymes but not do the reaction. So that's why you shouldn't eat cadmium or mercury. That's why they're poisonous to us. Now, if your cofactor is not a metal but it's an organic molecule, we call those coenzymes. And you have two different types of coenzymes. If your coenzyme binds and unbinds, we call that a co-substrate. While if your coenzyme's always bound, we call that a prosthetic group. So they are permanently associated with your protein, and they bind usually through covalent bonds. We've already seen one of these. Heme is a prosthetic group. Heme is always bound to myoglobin or hemoglobin through covalent bonds. Heme will never come off. And so when we're talking about enzymes that have these prosthetic groups, we have different names. A holoenzyme is an active enzyme that has its cofactor bound, so it's catalytically active. While an apoenzyme is just the enzymatic portion, it's just the protein portion after your cofactor has been removed. Now, cofactors are usually chemically changed during the reaction. That's why they're there. And they have to be regenerated before you can do another reaction. So the cofactors usually change, and it has to be changed back before a second reaction can take place. That's it for this video. I will see you in the next one.